solve the game of life. Hi everyone, we're here today for another Exponent mock interview with Simon. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. Hey, thanks so much for being here with us today, Simon. It's awesome to have you back again. Would you quickly introduce yourself to our viewers?
Yeah, definitely. Hi, everyone. My name is Simon Ayzman, and I'm currently a software engineer at Google. I've previously worked at Spotify, at Etsy, Bloomberg, and Foursquare, and I received my MBA and Master's in Computer Science from the University of Chicago. And I'm looking forward to being here.
That's such a diverse array of experience, and I'm really excited to see how you solve this problem. Okay, so let's get into it. So the question today is solve the game of life. And so the way that you play this game is that it's a board game that's made up of an M by N grid of cells, where each cell has an initial state. So either it can be alive, which will represent with a 1, it can be dead, which will represent by a 0, and then each cell interacts with its 8 neighbors, so the horizontal, vertical, and diagonal neighbors, according to a set of 4 rules. First of all, any live cell with fewer than 2 live neighbors will die, basically by underpopulation. Any live cell with 2 or 3 live neighbors will live on to the next generation. Any live cell with more than 3 live neighbors dies by overpopulation, and then any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. So then you can create the next state by applying all of those rules simultaneously to every cell in the current grid, so where births and deaths occur simultaneously. So if you're given the current state, I want you to basically return the next state.
Got it. Yeah, I think I remember something like this like many years ago in like a computer science class. We probably talked about it.
Yeah.
But would it be okay to get like a version of the question that kind of has all the rules enunciated?
Yes, sure. Sorry, what do you mean by that?
Could we just like get the question like shared so we have like the rules in front of us? We have this M by N grid, and we have to change it according to these rules.
Mm-hmm.
Got it. All right, I think this makes sense. In terms of the output, like in terms of getting the next state, do you want me to return an entirely new copy of the grid with the updated values?
I'd prefer if you could do it in place.
Sure. Yeah, I think that makes sense. We probably want to be space saving. Would you be able to show me some example input and what we think that the next state would look like?
Sure, yeah. So I have an example. I'll put that together with the instructions.
Yeah, this is starting to make sense. And this might be an assumption, but the cells outside of the grid, are we just assuming that they're considered dead, that they have a 0 value?
Yes.
Why don't we go through some of the actual cells and kind of reason about why they changed the way they did? So if we kind of look at the initial state, this cell, for example, it died and turned into a 0 over here. And the reason for that is because of rule number 1, because it only has 1 live neighbor around it, and we need 2 or 3. Okay, so that makes sense.
Mm-hmm.
Let's look for a cell that stayed alive. So for example, something like this cell and this cell, this one has 3 live neighbors. This one has 2 live neighbors.
Mm-hmm.
And that's the reason why it stayed alive into the next generation.
Right.
Now we see one cell that actually became alive. So this 0 right here turned into this 1 because it has 3 live neighbors. Okay, yeah, that makes sense. So that's an example of rule number 4. I don't know if I see an example of rule number 3, but I think it makes sense, right? If there's ever 4 or 5 or more alive neighbors, it would die.
Yep.
It would die. Okay, I think this makes sense. So I think I have an idea of what the algorithm would be. Basically, I would go cell by cell, row by column. I would look at each cell's neighbors, and then I would update its living status depending on what the neighbor count is. But okay, I think I'm kind of I'm starting to see what the issue with the problem is. What the crux of the problem is. You basically can't update the cells themselves to their final dead or alive status and then also simultaneously count them as neighbors for the other cells. I think that's
It's in place, right?
right, exactly. Because, if I go cell by cell from the top to the bottom, if I accidentally, kill this cell right here, I'll incorrectly count the number of alive neighbors in its respective neighbors. So
Right.
I kind of need to find a way to, as the problem says, to kind of do it simultaneously.
Yeah, exactly.
Okay, so it seems then that we have to do it somehow in multiple steps. We can't just do it all at once towards the end. Like you said, we kind of, I don't really want to make a full copy of it because we are trying to save space. And like you said, we don't need that secondary copy if we're doing it in place. So I think what I need to do is I probably need to update each cell to some sort of an intermediate state and then update it to its final state.
Okay, so what would that intermediate state look like?
Yeah, I suppose that the intermediate state somehow needs to encapsulate both the previous state and the next state. So what it was before and what it's going to be. I guess one approach would be to just replace all the cells with tuples, where we could have like the first entry be the old living status and the second entry be the new living status.
Okay, so I guess, well, technically that would work. That's almost equivalent to just like using another array. Then it uses a lot of extra like storage. Is
Yeah,
it
you're right.
possible to do it without tuples?
Yeah. Is the idea there basically to keep the sort of like the types consistent too, like only to use integers in this grid?
Yeah, exactly. Yeah.
Got it. Yeah. Okay. I mean, that makes sense. Yeah, the tuple approach is kind of, yeah, it doubles the space. If that's the case, if we're only allowed to use these integers, basically, then I suppose we just have to make our own mapping, if that makes sense. The same way where we would represent the same information of like this transitory state without a sort of like other structure. So for example, I think it helps to be specific here. So let's take a look at some examples. So you have the state where a 0 becomes a 1. We have the state where a 1 stays a 1. We have the state where a 0 becomes a 0, and then we have the state where a 1 becomes a 0.
Yeah. So
okay.
Total.
Yeah, I think that's like the closed universe of what we have. So how about this? Why don't we just actually set these sort of states to have their own mapping? Maybe I can rearrange these just so it's a little bit clearer. So 0 to 0 would be 0. That makes sense. 0 to 1. I don't want to confuse that and make that a 1. So maybe a 1 to a 1 would be a 1, so it stays alive.
Okay.
A 0 to a 1 would be a 2, so it becomes alive. So let's switch that order. And then a 1 to a 0 is a 3.
Yeah, that makes sense to me.
Yeah, I think that's a reasonable mapping. So then to kind of like re-summarize the approach, what we're going to do is we're going to have this two-step approach where in the first step, we iterate cell by cell and we reach this intermediate state of 0s, 1s, 2s, and 3s. And then we would basically reiterate through the graph and kind of clean up all of those 2s and 3s to convert them to what they actually mean. So a 2 would be converted to a 1, a 3 would be converted to a 0.
That sounds like it would work to me. Yeah. Do you want to get started with writing the code?
Yeah, awesome. Let's just jump right into it.
Okay, great.
Let's comment that out. Let's give ourselves some space to work here. Game of life. It's very profound. Okay, so we have this grid. We want to return the grid back. Basically, the first thing I'd want to do is basically iterate over the grid itself. So
Yeah.
for row and enumerate grid. So this would give me the index and the actual row itself for the column, and the cell itself in enumerate row. So this is the actual step where we want to kind of convert it. So I think what I'm actually going to do here, when we're converting it, we need to count the neighbors around us. So if we kind of look at this initial state, it would probably help us if we have another helper function called get live neighbors. So what this will do is basically this will iterate over all of our neighbors and count their values. So this will do something like live neighbors equals 0. Get live neighbors would have to take the grid, the row, and the column. And then it would kind of iterate over all of its different 8 neighbors. So let's actually give ourselves a helper function or a helper tuple here. One good approach would actually just be to provide the offset, basically. So something like 0, 1, 1, 0, 1, 1, -1, -1, 0, -1.
And what is the data type of grid here?
So the data type of grid here is basically a list of integers, right? Is that a fair representation?
Mm-hmm.
Yeah. And directions here basically just represents that offset. So we're going to be using that to, instead of writing 8 different checks, we're going to do a for loop where we can iterate over directions.
Yeah, that makes sense.
So for, let's say, direction in directions. So I didn't finish this, but just to kind of give a view into what that'll look like. -1. Okay, and then the last one would be -1, 0. Oh, I already did that. -1, 1, and then the opposite of that. 1, -1. Okay, so that's 8. Yeah, okay, that makes sense. So basically for direction and directions, what we're going to figure out is what the actual row offset at that point. So row offset equals and then what that tells us is the actual value of the neighbor itself. So we would do neighbor equals grid row offset call offset. So what we can do now is we can actually do this check like we said. Now, normally we would just count the ones, but we actually have to do it according to this mapping here. So if neighbor equals 1 or neighbor equals, let's see, what was our original mapping? A 3, that would be that case. Then we can simply do live neighbors plus equals 1. And then we return the live neighbors. Okay, so that's what we would do here. And then inside of this original function, we just use that helper. Okay, I think this makes sense. And then now is when we can actually implement the rules. So based on the number of live neighbors that I have, we change the cell value itself. So
get live neighbors assumes that you've already have the intermediate state then.
Yes, exactly. So there could be a potential situation where one of the neighbors themselves, like let's say we're at this cell right here. when we would look back up at some of these cells, they might actually be a different value. So for example, this 1 would have converted to, I guess, a 3, most likely, after this situation.
Yeah.
So we want to make sure that get live neighbors properly encapsulates that information.
Yeah, okay, so is there like a function somewhere that actually populates the intermediate state of like the 0 through 3?
Yeah, that would happen right here inside of this for loop. So here I would have the rules, like if the live neighbors, for example, is less than 2, then I would change grid, basically.
Okay, I meant like, so here you're checking like if neighbor equals 1 or neighbor equals 3. So that assumes that you've already converted the 0s and 1s to 0 through 3s.
Yeah.
So that would have to happen before you call get live neighbors, right?
Yeah, I think it can happen at the same time.
Okay, yeah, let's see how you would implement that. I think I'm a little bit confused by this part.
Okay, so at this point, what we're doing is we're checking the live neighbor count. So in this case, we can, take care of rule number 1 if the cell dies by underpopulation. So that would be when it goes from a 1 to a 3. So then what we would do here, we would do something like grid call index equals 3, for example. We can ignore the case. We can ignore case 2 because that basically tells us that nothing has changed. For row 3, what that basically for rule 3 rather, we can check if there's more than 3 neighbors. So if live neighbors is greater than 3, then that would basically change to a different number. Let's see, according to a rule, if it dies, it goes from a 1 to a 0. I'm sorry, if it goes from a 1 to a 0, that would also be 3. So we can probably combine these two cases. Let's just confirm that that's the case. Fewer than live, dies. Yes, so basically rule 1 or 3. And in another scenario where we have exactly 3, so if live neighbors equals 3, then what that basically tells us is that we would have to be able to check, if the current cell that we're at is a 0 or a 1. That's like the kind of condition that we're missing here. So if the actual cell itself equals 1 and both of these cases are true, then we have to, do this step where we flip it basically. So, and in the opposite case where we have exactly 3, so if cell equals 0 and live neighbors equals 3, then that means we kind of actually flip to an alive state. So that would be situation 0 to 1, that would convert to a 2. So I think this kind of encapsulates the set of rules basically. With rule number 2, a 1 would continue on to the next generation. That's this one. And then if there are more than 3 live neighbors, it dies. Yeah, okay, so that encapsulates that rule. So one thing that we're actually missing here is a boundary check that actually occurs to me. So for example, get live neighbors, it's potentially incorrectly going over all of the directions. So what we have to do is we have to check that we're actually not, going to throw an exception for index out of bounds. So let's give ourselves another helper function. So is in bounds. And that could be something as simple as, checking the size of the grid. So if row is less than 0 or call, or actually inbounds means has to be positive. So row is greater than equal to 0. Gotcha. So then what I would do here is if is in bounds, or I would say if not is in bounds, grid, offset, call offset, then basically I would continue. So that gives us like an early exit condition. Otherwise, we know that we are in bounds, and therefore we can properly calculate this.
Yeah, perfect.
And then finally, I think the last thing that we want to do is we want to do a cleanup where basically iterate over the cells and fix them. So.
And by fixing, you mean converting 0 to 3 back to the original zeros and ones?
Yeah, exactly. So we could have something similar to this. And then we just check what the cell value is. So if cell equals, for example, 2, then we want to convert it to a 1. Then what we do is grid. Becomes a 1. Also cell equals 3. Then we convert it to the other one. To a 0. And I think that overall this should work. I think maybe this gives me some pause, like maybe the rules need to be properly encapsulated, but I think this looks almost there.
Yeah, so I did have a point of clarification. So when you first
Sure.
get the grid only contains zeros and ones, right?
Yeah.
Right. So then the first function that you call on it is get live neighbors, which then like pulls out individual cells from that grid, and it checks if the neighbor equals 1 or neighbor equals 3. But at that point, the grid only contains zeros and ones. So I'm confused about why there's this like neighbor equals 3 case.
Yeah, so we can think of a scenario where when we do go cell by cell, like a good example of that would be if I like scroll up to the initial state up here. So let's say I'm kind of showing this as my in place grid. This one would become, let's see, it would become a 3 because it dies. It's underpopulated. So once I reach this cell, it changes to a 3. When I reach this cell, it stays the same. When I reach this cell, it would count its neighbors. So it would basically see I have a 1 over here, a 1 over here, and a 1 that used to be kind of over here, right? So that would be this case. So, so even though we're kind of doing it in place, we still want to properly count that 1 over here so that we can properly flip this to be a 0 to a 1, which is a 2, right?
Yep. Perfect. Yeah. So it's because it's going in row major order, and
right.
And you know what the mapping is. Okay, great. Yeah, and you had wanted to make a point about the coding?
I'm sorry, what was that?
And you had wanted to make a point about like how to clean up the code?
Yeah, so in terms of cleaning up the code, I think these helpers definitely help. I think, I don't know if we need to necessarily clean up this aspect of it because we are like redoing it. Maybe we could put this into another function of some kind that kind of cleans it up. That would be a good candidate for that. But this looks pretty close. I think it could be worth it to like maybe do a unit test or two.
Yeah, I'd love to see that.
Awesome. So let's actually take these data sets. So that's the first one. That's the second one. So this is the initial state. Oops. Sorry about that. This is the initial state. Expected next state. And that would be the same thing. So what we're looking for at the end of this unit test is basically like a true. So what I want to do is game of life on the initial state. Past test. game of life of the initial state equals the expected next state. And let's just print whether it passed the test. Okay, so let's run that. Okay, so basically we're kind of improperly iterating over this somehow. Let me see. Maybe I just can't see it. Ah, there it is. Yes, I forgot a comma.
Oh, there we go.
Amazing, amazing, yeah. Okay.
Perfect.
All right. Okay, it failed somewhere. So somewhere we're improperly actually printing out or we're improperly setting the cells. So the way that I would probably test this to figure out where is, I'll print the expected next state and I'll print my current result, and then we'll see where that gets us.
Yes.
So actual next state is this. So what we want to do is for row in actual next state, print row. So that's it'll allow us to test it. And similarly, let's see what it looks like. So we know what we want it to look like. Oh, well, none type is not iterable. So that means
it's not actually returning anything in that function right now.
that makes a whole lot of sense. So what we want to instead do is we want to have the initial state. What I'm going to do is I'm going to in place grid equals initial state copied. And then what I'm going to do is actually, I'll call it like this. So expected next state. It passed. All right, excellent. So the issue basically there, like you said, game of life is doing it in place, and I was getting none back, so that's why I was failing.
Great. Okay, so are there any other test cases that you might want to test?
Yeah, so I mean, a great one, we want to test corner cases where it's all zeros. Another good one is when it's all ones, because it would be all overpopulated. So we'd want to see that basically all becomes zeros again. So that would be a good test case.
You also mentioned earlier on that this test example doesn't actually cover all the rules, right?
Exactly, yeah. So rule number 3 was the one where we had a situation that something should die by having more than 3 neighbors. Mm-hmm. So we can test that out by maybe putting like another 1 over here or something like that.
Yeah.
Okay. Let me copy this just so it's separate for us. So if we have this one right here, let's actually think that through. So if this was a 1 right here, what should die? This cell should die. It should turn into a 0. And yeah, I think that's it. Like this would be the only difference. Maybe some of the other neighbors will actually change because now you have another alive neighbor. So this one might die. This one will actually become alive.
Yes.
This is the thing about the rules for this, that you kind of
it's a change.
Ever changing, exactly. So like I've seen the simulation of it, and it just kind of it's doing a lot of stuff, like where it goes to infinity. A lot of changes happening all at once. Mm-hmm. So in this case, this cell would die. Let's actually change it. So this is case 1. This is case 2. All right, so if we made this a 1, let's see. So this would still be dead afterwards. This cell would still, it would still be alive actually because it has 2 alive neighbors. This cell would spring to life because it has exactly 3 neighbors. This cell would, let's just set these all to be 0, just so it's a little clearer what I'm reading. So this cell right here, it would stay dead. This cell right here, it would definitely die. This cell right here, it would also definitely die. This cell right here, it would stay alive. It has 2 alive neighbors. This cell right here, it would die. This cell right here, it would stay alive. This would be a 1. This cell dead. This cell becomes alive because it has exactly 3 neighbors, and then this cell would stay dead. So I think this would be our expected output from that other case.
Yeah, I think I agree.
So let's set that here. All right, let's try that again. I should see hopefully 2 passes. Yep, awesome. Looks good.
Great. Okay, fantastic. So I think this is a good place for us to pause then and debrief a little bit. I'd love to hear from you what you think went well and what do you think you would want to improve? Because this is honestly fantastic.
Yeah, so I think one thing that I did well at the outset was that, there are some aspects that I wasn't sure about in terms of the problem. So asking some clarifying questions as I went along, as I sort of adjusted the algorithm and realized that something wouldn't work. So asking those clarifying questions was definitely helpful. I think another thing is that I kind of took your suggestions in terms of what wasn't quite working with that initial approach, and I kind of adjusted as necessary. In terms of what could have gone better, I think that I tripped up on certain aspects of the code, especially when I was unit testing, or for example, I had the boundary condition that I didn't quite realize was an issue until later into coding. So that could have maybe gone a little bit smoother.
Yeah. Okay. Yeah, those are all really good points, I think, and I agree with a lot of that. I think there was a lot that you did really well in your interview, so I want to start with that first. You had some really great clarifying questions in the beginning that I think totally changed your implementation in the end. Like, had you not asked about whether or not it should be in place, your initial solution might have been much less efficient, actually. So that was awesome. And then you, once you decided that you wanted to use an in-place implementation, you had the clever insight that in order to do this, the main difficulty is that it's hard to simultaneously read and edit the same array at the same time.
Yeah.
Right. And then overall, I thought that the code itself was really modular and in general had descriptive method and variable names, which is also important. And you were really good at using various Python primitives, using the array slice to basically get a copy of the array. And in general, I really like that you did such a thorough job of testing with many different test cases, and you seem to know how to debug too, and identify the specific cases where your code might go wrong. And you caught your own mistakes as you went along, identifying the boundary condition. So I didn't need to point that out to you. So that was awesome. So I think one thing that could have been even better, especially because in interviews, they tend to be a little bit more particular about this, is coding style. So I think you mentioned this a little bit earlier, actually, but we never sort of got to it, is that for the mapping, so the mappings from the zeros to ones to the intermediate mapping, custom mapping from 0 to 3 and then back, we could probably implement those either as dictionaries or helper functions. And that would probably get rid of a lot of these if cases that you see throughout the code and make it a lot easier to read.
Yeah, that's true.
Yeah, and then another thing specifically with Python too, it's often in many style guides that you should use type hints for the arguments and also like some method comments, right? Especially for code like this that can be a little bit confusing if you don't entirely know what the algorithm is beforehand, especially for
Yeah.
for loops where you're simultaneously like editing and reading the grid at the same time. So the contents of the collection that you're iterating through is changing as you're iterating through it. It's good to include a comment there indicating that that will happen, you know?
Yeah.
Yeah, but I think other than that, it was excellent. Thank you so much for joining us today.
Yeah. Thank you. Really appreciated the time.
Yeah, and this is such like an interesting question. So thanks everybody for watching, and good luck with your upcoming interviews. Bye, everyone.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.